Okay, so today we're going to put everything that we've been going through together and look at relative velocity and projectile motion. So when we're looking at the idea of relative motion, what we're really saying is that frame of reference is important. So I could ask you the question, are you moving right now? Okay, well, you could say yes, your hand's moving as you're taking notes. You could say no, you're not, because you're not up walking around. You could say yes, you are, because you're on the earth and the earth is rotating. Okay, you could say no, you're not, because your position relative to the person sitting next to you is still the same. So when we're looking at motion, we have to keep in this idea that motion is relative. Okay, are you moving fast? Are you moving slow? Well, compared to what? As you're driving down the highway, if you're driving at 65 miles per hour, those signs look like they're passing you by really quickly. Why? They're standing still. But if you're in the car and you just look at just the car around you, the person sitting next to you, you don't look like you're going 65 miles per hour because you're both going 65 miles per hour. So whenever we're talking about motion, we have to be careful with what is our frame of reference. What is our velocity relative to? Relative to what? So here's an example of it. You have a person walks towards the front of a train at 5 kilometers. The train is moving at 80 kilometers with respect to the ground. Okay, so that's important. They're not telling you how fast the girl and the train are moving together. They're telling you if you were standing on the side of the road watching this go by, you would see that the train is moving at 80 kilometers per hour. Okay, so we want to know what is the person's velocity with respect to the ground. So how fast does a person look like to the ground? Okay, well, the girl is moving 5 kilometers, okay, to the front of the train. The train is moving forward, so also in the front direction. So they're moving in the same direction. Okay, so you're going to add them together. So from the outside, it would look like the girl is actually moving at a speed of 85 kilometers because she's on the train's moving 80, but she's moving 5, so she's actually looking like she's moving 85 kilometers per hour. Now, relative to the other passengers on the train, she only looks like she's moving 5 kilometers per hour. Okay, think about it when you pass somebody by in the car. If they're going in the same direction and they pass you and they're going 80 and you're going 65, they don't look like they're going that much faster than you because you're both going in the same direction because you're now moving. So your reference is not some stationary object. So to each other, they only look like they're going 15 miles faster than you. The car going in the opposite direction, though, because of how you're meeting them, they're going to look like they're going by even faster than what you would expect because you're heading east, they're heading west, so you're going to pass each other even faster than it does like the object on the ground. Okay, so just be careful as you're going through these examples. What is your velocity in reference to? What is your position in reference to? I could say right now that some of y'all are 20 feet tall. Okay, there's no giants in the room, but you don't know what my reference is. Maybe my reference is to the ground outside. Okay, I could say you have no height because you're in reference to your chair because your butt's on your chair. So just be careful when you're looking at motion. What are you saying it's relative, or what is it saying in reference to? Okay, so we see the same sort of things if you're talking about like boats or trying to swim across a river. So here you have a boat that's trying to make it across the river. So when you look at this top picture, okay, the boat actually is going to have, so the water's going down. The boat wants to go straight across, but since the river's pushing it down, okay, in this picture actually to the left, you have to actually steer it more towards the right, so that way you're aiming towards the right, but the water's pushing you to the left, so that way it'll actually direct you straight. And to an outside observer, okay, the person that would be across the river, they're not going to see that your wheel is slightly turned. So to them, you're moving straight. You being in the boat, you can tell you're moving at an angle. The river is clearly moving down, but they see you as moving straight because you've angled it, okay, as you're looking at it. The same thing is true with airplanes. Okay, so whenever you're looking at an airplane, they actually have to take that wind into account. And if it's a really small airplane especially, or if a plane comes into contact with a strong wind, can veer them off course a little bit, which is why if you've ever looked at some of the flight tracker apps that are out there, flight tracker websites, and you watch someone's route that they're taking to go from one place to another, they don't fly directly at that point because they have to account for the wind. Okay, if you fly like in this picture here, if this boat goes straight across and the river's pushing it to the left, then that water is going to push them down and you're going to end up somewhere further downstream. You're not going to end up where you want to. And the same thing is true with airplanes. And the windier it is, the more you have to adjust for that, the more you have to correct as you're looking at your velocity and where you want to end up. Okay, so this is just something, anytime we're talking about velocity, displacement, things like that, you have to be careful, what are you in reference to? So you're going to just want to make sure you state that on some of the problems, where are you defining it. When we do potential energy and roller coasters, it's really going to become important. So you'll just want to note that on the side of your paper, on your AP problem, something saying as my reference point is whatever, okay? All right, so projectile motion. A projectile is any object moving in 2 dimensions under the influence of the Earth's gravity, okay? And its path is going to be a parabola, okay? So you're looking at things that are going to be parabolic in nature. They're going to have that parabola shape. So some examples of this would be launching a ball, kicking a ball, throwing a football, serving in volleyball, serving in tennis, a baseball as it's being like thrown actually goes up and then comes back down towards the batter. Once the batter hits the ball, okay, a cannonball, all of these things are moving in 2 dimensions. But the key thing is in each one of those situations, once the action's been completed on them, so you kick it, throw it, launch it, it follows that parabola shape, okay, because it's acting under the Earth's gravity. So it's going to pull it down, but it's going to be speeding up as it approaches down and slowing down on its way up. So if you look at this picture, this would be for like of a ball bouncing, for example. You'll notice that the dots get further and further apart as it reaches down because it's accelerating due to gravity. On the way up, the dots get closer and closer together because each second it's traveling faster, so the amount of distance that it's covering in each second is going to decrease. And that's how you get that sort of parabolic shape. Okay, is as it travels on the way down, it's going to get further apart. On the way up, they're going to get closer together. All right, so when you're looking at projectile motion, okay, first thing is we're going to neglect air resistance. Okay, when you include air resistance, it just adds in as an additional factor. We'll work some problems later on in future units that deal with air resistance. So for right now, no air resistance. Everything's in a perfect vacuum. Okay, makes your life easier. When you're looking at it, you're looking at the motion before, only after the release and before it hits the ground. So you're looking as it starts moving. So if you're talking about like a soccer ball being kicked, if you're talking about like a goal kick, for example, that the goalie is doing, the ball is at rest initially, yes. Okay, granted, I agree with that. However, we want to start the motion as the ball kicks. So our initial velocity is not 0. It's literally how fast that's moving at like 0.00001 seconds. Okay, so how fast did he kick the ball with? And then the same thing on the other side of it. Our final velocity is not 0 for when the ball hits the ground again. We're looking at that fraction of a second right before the ball hits. Okay, if you think about it, if your velocity is 0, why does it hurt when you land? You're not moving. Okay, it hurts when you fall because you're hitting the ground still moving, and then you stop. So I want to know, how fast are you hitting the ground? Okay, again, you're going to want to analyze your horizontal and vertical components separately. Galileo came up with doing that, with analyzing things in separate pieces. In the X direction, okay, if you think about it, once the ball is moving, what brings it to the ground? Okay, gravity. If there's no air resistance, there's nothing else acting on it in the X direction. It's just floating in free space, basically. So the only reason that object is going to slow down or be brought to the ground is because of gravity. Gravity acts only in the y direction, so that means your acceleration in the x direction is 0. Since your acceleration is 0, that by definition means that your velocity is not changing. So the nice thing is once you figure out your horizontal velocity, it's the same at every single point that you can come up with. And again, you're talking about projectiles, they're under the influence of gravity, so that means your acceleration in the vertical is going to be gravity, negative 9.8 meters per second squared. Okay, since you have a non-zero acceleration, that means that your velocity is not constant. Okay, so it's going to be changing. The other thing to keep in mind is that it may be going positive, it may be going negative if you change directions. Remember that the positives and negatives on acceleration is in reference to direction. Okay, not thinking of increasing and decreasing. It's literally due to direction. Okay, and then finally, objects projected horizontally will reach the ground at the same time as ones dropped vertically. So if you look at this and you drop something from the same height that it's kicked out perfectly horizontally, they will land at the same time. Why? Gravity. What pulls an object down to the ground? Gravity. If you look at something that's kicked out to the right, okay, kicked out horizontally, initially in the y direction, it's not moving. So the only thing acting on it is gravity. Gravity is going to pull on everything the same, okay, as it pulls it down. Everything it acts on at negative 9.8 meters per second squared. So that means that they're going to fall at the exact same rate and hit the ground at the exact same time. And I'll post a Mythbusters video that you can watch as well, that they do a bullet drop with it. So that'll be in the next video that you can watch for this day. Alright, so your equations for projectile motion. In the horizontal direction, your acceleration is 0. Okay, since you're moving at a constant velocity. This, by the way, is the same graphic that was on the last slide, so if you want to see it a little bit better. Vertical direction, your acceleration is gravity. Your horizontal velocity is constant. And so your initial velocity in the x direction is going to be the same as your initial velocity in the x. So velocity in the x direction never ever changes. In the vertical direction, you'll notice that you have your three amigos as being the equations you're going to use. Okay, the negative here is just going with the negative 9.8, so it's changing the sign already. Don't put negative 9.8. Remember, your equation is plus AT, so it would be plus negative 9.8, so that's why it's a negative here. If that confuses you, don't use it. Same thing on this one, it's negative because of gravity. Same thing here, negative because of gravity. And then you'll notice in the horizontal direction, the only equation you can use is your equation for constant velocity. V equals delta x over t. Okay, it's just rearranged for x, okay, to find out that distance. A key thing when you're looking at this, okay, if you have an acceleration that is not 0, you have to use the three amigos. This equation, velocity is displacement over time, is only valid when your acceleration is 0. When you're literally moving at a constant velocity. So horizontal velocity is distance over time. Vertical, you're using the three amigos, the three kinematic equations. All right, let's say though if it's kicked out at an angle, okay? If you're kicked out at an angle, in this case now your initial velocity would be something other than 0. It's going to be a component. So if someone kicks a ball at 15 meters per second at an angle of 20 degrees, what you would have to do is figure out your initial velocity in the x and y. Remember, like I said, x's and y's must be kept completely separate. The only variable that is allowed to go in both columns is time. So if you think about it, your time, the time that it takes to travel this distance vertically is the same time that it takes to travel this distance horizontally. An object doesn't hit the ground and still keep falling. Okay, so your time is the only variable that's allowed to go in both x and y columns. Everything else has to be kept separate. So just like we did with vectors, the first thing you're going to want to do on a problem like this is take your initial velocity and separate it into its x and y components, because this velocity is going at an angle, so it has an x and a y component. Just said the only thing that can go in both columns is time. So before you even begin, find your initial velocity in the y and your initial velocity in the x. Okay, so that way, and then you can be done with it. On your way up, you'll notice that your vertical velocity vector gets smaller, and then 0 at the top, and then points downward. Okay, and still points downward. So what's happening in the vertical direction only, on the way up you're slowing down due to gravity. At the top, you actually change directions, and in that moment that you're changing directions, your velocity becomes 0. Think about a graph. If you make a graph of velocity versus time, and you're throwing something up, you would be starting in the positive x direction, heading towards 0 because you're slowing down. You pass by 0 and then continue to go down in the negative direction because your velocity is increasing. Your slope of that line for an object in projectile motion should be negative 9.8 meters per second squared. So this point right here would be as you're passing changing directions, you're passing the x-axis. So at this point, you've literally stopped for a split second in time as you're changing direction. So this would be at the highest point. So you would want to add that to your notes. At the highest point, your velocity in the y direction is 0. If you also notice something, your y vectors are the same size, just pointed in different directions. So at these 2 points right here, on the way up and on the way down, your speed is the same. Because if you think about gravity, gravity is going to slow you down at one rate, speed you up at that exact same rate. So when you're at equal heights, you have equal speeds. Equal heights, equal speeds. The difference, though, is going to be your velocity, because velocity is based on that direction. On the way up, your velocity is positive. On the way down, your velocity is negative, but the magnitude would be the same. Okay, so again, this also says if your ball returns to the point y equals 0, so once it hits this part on the ground, if you let the ball land, no one catches it in between, then that velocity here will be the same as the velocity over here. Only difference is on the way up it's positive, on the way down it's negative. Another thing to keep in mind, at every single point along the path in the vertical direction, I don't care where you are, your acceleration is gravity, negative 9.8 meters per second squared. In the x direction, if you look at your velocity vector, your x velocity never, ever changes. Okay, because there's no acceleration in the x, so your velocity is constant. So if I asked for the x velocity, once you've used this VO cosine theta to figure out what it is, I could ask you that x velocity at any point along the path and give me the same answer. It's not a trick question. It's the same everywhere because your acceleration is 0 in the x direction. Okay, again, at the highest point, your initial your velocity in the y is 0, and your horizontal velocity is just the only velocity that exists. Okay, so when you're at the highest point, your velocity is 0 in the y direction. Still is moving in the x direction, so it still has to have some velocity. Another thing to keep in mind is how you work these problems. You can separate it off into different segments. So if you wanted to figure out the time of flight, you could do the time it takes to go up and then double it. You could take the time that it takes to go down, double it, or you can set the whole time. So that's going to change what you make your initial and final velocities. If you work the way up, then your final velocity would be 0. If you work the way down, your final velocity or your initial velocity would be 0. And if you work the whole thing, then these two velocities will have the same magnitude, except for one will be positive and one will be negative. So your givens may not be the same as the person sitting next to you. Again, going back to what is your frame of reference? What's your initial? What's your final? Where are you defining that as? All right, so let's do an example. You have a football is kicked at an angle of 50 degrees above the horizontal with a velocity of 18 meters per second. Calculate the maximum height, and you're going to assume that the ball was kicked at ground level and lands at the ground. So if you start on the ground and you end at the ground, your total Y for the entire trip is 0. Okay, but I don't care about the total trip. I literally just want to know how high does it go. Okay, so the first thing I'm going to do is I'm going to separate my initial velocity into its X and Y pieces. So I'm going to do my equation V naught X is equal to V naught cosine theta. So 18 cosine of 50 is 11.6, and then I'm going to do the same thing for the Y. V naught Y is V naught sine theta, which would be 18 times sine of 50, which is going to give you 13.8 meters per second. Okay, so now that I'm done with that, I can literally ignore the 50 degrees and ignore the 18. Okay, I'm done with those. The fact that it says above the horizontal, that's telling you that reference. So you're starting at 0, go up 50 degrees, and that's where your ball is being kicked. Okay, if you want to draw a picture. Okay, so at the top, you have this equation. This is not the only way to do this, by the way. Okay, more than one way to solve this problem. So at the top, I know that I can use the equation V final Y is equal to V naught Y minus GT. Again, if you don't like using the minus GT, you can put plus AT. Just remember that it's going to be a negative sign in there. So I'm going to say that that's going to be equal to 0. Why? Again, at the top, my final velocity is 0. So I'm telling you this. That's where I'm defining my reference. So I can rearrange this equation and say that T is equal to V naught Y divided by G. Take V naught Y to the other side. That becomes negative V naught Y equals negative GT. Okay, and then divide. Again, I've included the negative sign right here. Okay, always as a key factor, time can never be negative. So if time is negative, then somewhere you missed a negative sign. Okay, along the path. So I know my time to the top is 1.41 seconds. So then I can use my equation for my height, plug it in and solve, and get 9.7. You could do the same thing if you wanted to use the third amigo instead. You could do VF squared equals V naught squared plus 2A delta Y. And then you would have only had to use one equation instead of two. Okay, it's totally up to you. You'll get the same answer. I don't have a problem which way you solve it. My rule is always don't break algebra and don't break physics. So as long as you keep both of those things in check, then you're fine. Again, here's my negative for my negative 9.8. It's out here in the middle. Okay, I haven't lost it or anything like that. You'll notice that your Y max is positive, as it should be, because you're talking about the maximum height. Remember, height is always positive because you're talking how far from the ground up. So since you're going up, it has to be a positive value. If you get a negative, something's wrong. Okay, so those are just ways that you can check yourself. Okay, so again, make sure you're showing all of your work and everything so that way I can see it. Make sure it's all detailed. Show me all your equations. Always show the original equation. Do not just write down the manipulated equation. So never start with T equals V naught Y over G. Okay, always start with that, because this equation is a situational equation. It's not valid all the time. So always start with the true equation from the equation sheet. Okay, don't skip steps. Okay, don't skip steps. I will mark off points for stuff like that. Okay, prove to me every step that you're doing. Okay. So Next we have to look at is the range. Okay, when you're talking about the range, what you're looking at it is that your range is your horizontal distance. So range is just another term for horizontal distance. How far did it travel in the x direction? Okay, normally you're talking about for the time that it takes from where it's shot off or kicked from to return back to the ground. Doesn't always have to be, but normally that's what we look at it. Okay, if it hits something a fixed distance away, then the time is determined by the x motion. Okay, so what that means is that if you kick a ball, okay, so in soccer, you're trying to take a shot on the goal, but the goalie catches it, it still had more distance to travel. It's not on the ground yet. So in order to figure out how long the ball is in air, you have to go back to that x value. You have to go to that range. How long did it take before it was caught? Okay, how far did it travel horizontally? And then you can use your vertical stuff. Okay, because if you took the time that it takes to go up and the time that it takes to go down and use that as your time, it didn't hit the ground. The goalie caught it. So you have to go by how far it was, or the time that it took until it hit something else, until the motion stopped. Okay, again, if your motion is on a level field, so it starts on the ground and it lands back on the ground, then your delta y is 0, because you traveled up, but then you traveled back down. So in the vertical direction, you didn't move, because you started on the ground and you ended on the ground. Okay, so this gives us a couple equations, so I'm going to show you the derivation of where they came from. So if you take your equation, this is just your second amigo, okay? If you don't want to write the derivation down, that's okay. It's always good to know. Okay, so if you're saying that it hits level ground, then delta y is 0. It starts on the ground, so that's 0. So you're left with this equation on this side. V naught yt minus 1/2 gt squared. What I can do is I can solve it for time. Okay, so take this v naught yt to the other side and then divide both sides by t, so I can cancel a t out. And I end up with this equation that t equals 2 v naught y over g. So then, if you remember, v naught y is really found, going back to your trig, is VO sine theta. So you can say that time is equal to 2 v naught sine theta, g. If you notice, your angle is normally given to you, your initial velocity is originally given to you, and gravity is a constant, you can find your time really quickly. Okay, this equation is not on your equation sheet. It will not be given to you. You can use it, but it's not given to you, okay, for it. But this equation is only valid if this statement is true, if the motion on a field is level when it hits. So if you kick it from a ground and it lands at any other height but the ground, this equation is not valid. Okay, it is very conditional specific. Okay, what you can do now is you can put this into your x equation to find the range. Remember, for the x direction, the only equation we have is that v equals delta x over t. So x equals vt. So what you're saying is, remember, your range is just your displacement in the x direction, so r is x. X equals v naught t. So what I can do is I can plug this 2 VO sine theta over g into my equation for t and get v naught x times 2 v naught y over g. Okay, and then simplify it and then break it down. So you get, okay, again, this v naught x becomes v naught cosine theta. V naught y becomes v naught sine theta. So I have two v naughts, so that becomes v naught squared. Sine theta cosine theta. And then this 2 out in front. If you remember your trig identities, 2 sine theta cosine theta can simplify down into sine 2 theta. So you can say that your range is equal to v naught squared sine 2 theta g. Again, a lot simpler, not based on time. So if it just asks you to find the time, you don't have to make a separate equation for it. Or if it just asks you to find the range, you can just use this one equation. Again, be careful. This only exists if delta y is 0. If delta y is anything other than 0, this equation is not valid. It is also not on your equation sheet, so if you don't have it memorized, you don't get to use it. You'll have to go back and use the amigos. There's nothing wrong with the amigos, they will work. Okay, so just be careful on these equations that are situational. Alright, so again, this just shows you that trig identity again. 2 sine theta cosine theta equals sine 2 theta, okay, for your range equation. Okay, these are just some things that you need to know. Okay, you will always have the greatest range at 45 degrees. Okay, so if you want to get something to travel the furthest, okay, if you want to kick a ball the furthest, you want to throw a ball the furthest, you want to hit the ball the furthest, if you're talking baseball, whatever, okay, hit it at a 45-degree angle. The reason for that is that if you kick it too high, if you go above 45, you're going to get too much height, not enough distance. If you kick it too low, like a 30, then you're not getting enough height to travel that further distance. And so what happens is you come up with this relationship. Okay, if you want to find out what two values will have the same range, take 45 plus or minus however far off they are. So if you're 10 degrees above 45, so if you're at 55, 55 and 35 would have the same range. Okay, if you could do the same thing, 85, which is 40 above, would have the same range as 5. So the same number above and below 45 will have the exact same range. So if you're 2 above, 2 below would have the same range. Okay, so 15 above and 15 below are both going to have the same range. Again, the reason why for this 30, you may be thinking that 30 degrees is lower, so closer to the x component, so its x value is going to be higher. It doesn't, it's not in air long enough to reach its full potential. Okay, in order to travel really far, you have to go high enough, but not too high. Okay, so there's that catch range. So 45 degrees is your maximum range. Again, when you're looking at your range, okay, this equation is very situational. If it says that it hits anything else but the ground, if it's kicked from the ground, it has to land on the ground. If it doesn't land back on the ground, don't use this equation. It's null and void. Okay, you'll get the wrong answer. All right, so now we're going to calculate the range. So going back to that same problem we did earlier, you have a football is being kicked at an angle of 50 degrees, okay, and I want you to calculate the range. Again, that last statement, assume that the ball was kicked at ground level and returns on ground level. Key statement. Okay, so again, you're going to assume that the time going up equals the time going down because gravity is going to slow you up and speed you up at the same rate. So for range, we calculated this 1.41 seconds earlier. That was the time that you got. But that was the time to the maximum height. So that means if it takes only 1.4 seconds to get up, it should take me 1.4 seconds to come down. So my total time is 2.82 seconds. So then, remember, my range is equal to my velocity, or is equal to my horizontal displacement. So x equals v naught t. So that 11.6 that I found earlier, using that 18 cosine of 50 times 2.82 will give me my range of 33. Or you can use the range equation and do VO squared sine 2 theta over G, 18. You'll notice on this VO, it is VO. It is not V naught Y, it is not V naught X, it is the total initial velocity. So it'd be 18 squared times sine of 2 times 50 divided by 9.8, and you'll also get 33. Okay, so I don't care which range equation you'll use. Sometimes you may find that it's easier to use one than the other one. In this situation, I think since you've already solved for time first, like we did earlier, this equation is easier just because it's multiplying two numbers. If they didn't ask for you to find time first, then sure, go ahead and use this range equation. Then that way it makes your life easier. You don't have to use multiple equations. It is just up to you, okay? Whichever equation you want to use. Okay, now we're changing the problem. So same problem, same initial settings, only now it hits a window in a house that is 25 meters from where it was kicked. How high was the window above ground? So now we can't use that range equation. I'm telling you the range, that it's 25 meters from where it's kicked, but I can't go back and use that range equation because I'm hitting a window, not returning back to the ground. So I'm going to end up with a delta y value that's not 0. Okay, so again, I have my initial velocities from earlier. So the time to hit window, I'm going to use my x values first. So v naught x equals x over t. So I'm going to solve that first for time. So time is x over v naught x. So 25 divided by 11.6 is going to give me 2.16 seconds. If you look back at your previous answer for the total time of flight, you got 2.81. You'll notice they are different. Okay, it's above, the time is above that time value that we got to reach the max height. So that means that the soccer ball, or the football, excuse me, is hitting the window on its way down. It's already reached its peak and now it's hitting somewhere on the way down. Okay, but it hasn't hit the ground yet because our time is different. Then I can go back and use one of my amigos to find my delta y. Only now I'm going to plug in my time to hit the window, so 2.16. Notice I'm still using my v naught y. Okay, in here, since I'm solving for a y variable, I have to use my y, all my y variables. Okay, things have to match. If you're using x's, you stick with x's. If you're using y's, stick with y's. The only one that's allowed to go both ways is time. Okay, that is it. And so you'll get a height of 6.9 meters. If you got this y value to be higher than what you got for the maximum height, you are wrong. So in these multi-step problems, there's checks built in for you as a way just to make sure you're on the right track as you're working through these problems. Okay, again, you don't have to use the range equation. You don't have to use that special time equation. Everything that we've done today can be used using vectors and the amigos. Okay, so there's not really anything new today. We're just looking at it in a different manner, a different pattern. Okay, so now I want to know what is the final velocity and the angle that the football hit the window in the previous example. You're probably sick of this problem by now. Okay, I like these problems because, as you'll notice, I can change it up and ask the same question millions of times. Okay, so know how to do this problem. So I know that my time till when it hits the window is 2.16 seconds. So I'm going to use my first amigo. Okay. This velocity that I'm going to use here is my total initial velocity. I traveled initially on the way up, so I'm still leaving this positive, gravity's still negative, and this is my time to when I hit the window. So I get negative 7.37. Again, not the only way to solve this. Okay, not the only way to solve this. There are several different ways you could solve it. So now that I know my final velocity and the y, okay, I have to figure out my total final velocity. So I know my velocity, final velocity in the x, because remember your velocity in the x never changes. So I'm going to use Pythagorean theorem to figure out my total final velocity. So 11.6 squared plus negative 7.37 squared. And that's going to give me a total overall velocity of 13.7. So when this football hits the window, it's hitting it with a velocity of 13.7 meters per second, but I have to figure out my angle. So I'm going to do tangent of y over x and come up with an answer of 32.4 south of east, which is really 327.6 degrees. Because if you think about it, you're hitting it on the way down. It's traveling to the right. Normally, unless it states otherwise, with all projectiles, we always assume projectiles are being launched towards the right. So everything will stay in either the first or fourth quadrant, because it's either going up into the right or down into the right. So since I'm it's in the down portion of it when it hits the windows, I'm in the fourth quadrant. So it's going to be south of east, or 327.6 degrees. Okay, and I'll accept either one of those. All right, next one. Okay, so now we have something being dropped. Okay, so you have a rescue plane wants to drop supplies off to an isolated mountain climbers on a rocky ridge 235 meters below. If the plane is traveling horizontally with a speed of 250 kilometers per hour, which is 69.4 meters per second, how far in advance of the recipients the horizontal distance must the goods be dropped? Okay, so they're telling you a couple things. They're telling you that it was dropped, since it says it wants to drop the supplies. Anytime it says dropped, that means that your V naught Y is 0, and your V naught X is going to be the speed that the plane is traveling with. So 69.4 meters per second. Make sure you can convert this from kilometers to hour to meters per second. You should know how to convert. I'm not going to teach you how to convert. You should know how to do that by now. If you don't, you need to learn. So I'm going to use my second amigo. Y equals Y naught plus V naught T plus 1/2 AT squared. I'm starting at an initial height, so that's where this 235 comes in. My initial velocity is 0, so 0 times time is 0 minus 1/2 GT squared. And then that has to be equal to 0 because my final height is 0. So I rearrange that for time. And I get T equals 2 times 235 divided by 9.8, which is going to be 6.93 seconds. Then I can plug that time frame into my X equation and get 481 meters. Okay, sorry I got a little lazy with my work on the last slide a little bit. Make sure you show all your work. Okay, don't do like I did over here for the Y direction. This is bad. Make sure you show your initial equation. Show this equation. Tell me what variables those are. Okay, don't skip steps like I did on this one. This is what happens when you have kids. You get to skip steps occasionally. Because my son was probably crying when I was working on this. So, okay. Next time you're doing a lab over this is probably the hardest part of the unit. So make sure you practice these problems. The thing I like about it is, again, there's no new equations. but they just take time. So make sure you practice them, work them different styles. Okay, pay attention to all the conceptual stuff. Gravity in the y direction is always negative 9.8 meters per second squared. Your velocity in the x direction is always constant. If you're solving for a variable in the y direction, you're using the amigos. If you're solving for a variable in the x direction, you're using velocity as displacement over time. Your velocity at the highest point in the y direction is 0. If you start and end at the same point, then your delta y value is 0. So little things like that are going to make your life better if you remember those. And again, don't be afraid just because you solve a problem differently. Don't break algebra. Don't break physics. Okay? And you're okay. And no, your answer is not, I get to come up with my own new equation. Okay? That's not the right answer. Okay? Show all of your steps. Show all of your work always.